So imagine trying to fix a misfiring car engine by only changing the brand of gasoline you put in the tank. You're endlessly swapping out the fuel, which, in the AI world is the text of your prompt,
Right.
without ever actually popping the hood to look at the spark plugs or the fuel line or the cylinders. I mean, no amount of premium gasoline is going to fix a physically disconnected spark plug.
Exactly. It's just inherently the wrong intervention.
Yeah, and that is exactly what we've been doing with AI optimization. But the paper we are looking at today on AI paper slop completely dismantles that approach. It's called FAPO, Fully Automated Prompt Optimization of Multi-Step LLM Pipelines, coming out of researchers from Foundation AI Cisco Systems and Yale University.
And honestly, if you are an ML engineer building compound AI systems right now, you really need to pay attention to this core insight.
Yeah, lay it out for us.
So FAPO is a state-of-the-art framework that actually deploys Claude Code as an autonomous agent to optimize entire multi-step LLM pipelines directly inside a standard code base.
Directly in the code.
Directly in there, it evaluates your pipeline, it inspects the intermediate steps, and proposes these highly scoped changes. It starts by optimizing prompts, but if its attribution engine proves that prompt tuning isn't enough, like if it can't fix a bottleneck, it will literally rewrite your LangGraph chain structure.
Wait, literally rewrite the structure?
Yes, and the results are wild. Across 6 benchmarks, FAPO beats the baseline GPA optimizer in 15 out of 18 model benchmark comparisons. It delivers a mean gain of 14.1 percentage points.
That's significant.
Oh, but it's better. On tasks requiring structural code changes, it achieves this massive 33.8 percentage point mean gain.
Wow. Okay, so for the technical folks watching, this really marks the definitive end of, vibes-based manual prompt tuning.
Totally. Vibes are out.
Right. It's the shift towards systematic, pipeline-aware code workspace optimization. Because as the workflows you build get more complex, traditional optimization paradigms, they just hit a ceiling. I mean, tools like DSPy or GPA are incredibly powerful, but they operate within this strict boundary.
Yeah, they optimize instruction strings inside a fixed program.
Exactly. And a modern multi-step pipeline is compound. You've got a retrieval node, a reasoning node, and a formatting node.
Which, creates a massive blind spot.
Yeah.
Because if your multi-step pipeline fails to deliver the right final answer, a traditional prompt optimizer just inherently assumes the reasoning instructions need tweaking.
Right. It's just tell the model to think step by step.
Yeah, or be more accurate.
Yeah.
But the failure might have actually been a missed retrieval step way upstream. The model can't reason about context it was never given.
You can't analyze what you don't have.
Exactly. Current optimizers do not inspect those intermediate step-level failures inside the code workspace. They just blindly tweak the text of the final reasoning prompt and cross their fingers that the overall output improves.
But FAPO changes the objective function entirely.
It does. It treats the pipeline as an inspectable assembly line.
And I think that distinction is critical when we look at how models are evaluated today. We see tools everywhere like LLM or Agent Bench.
Oh, sure. Standard benchmarks.
Right. But those are designed to measure the raw capabilities of a base model. FAPO is doing something different. It's optimizing the design of a fixed pipeline. And the paper draws a really sharp line between this and adversarial search too.
Like red teaming.
Yeah, exactly. In red teaming or jailbreaking, the tools use a best of N search. Their goal is purely existential. They just need to find one successful exploit out of hundreds of attempts to prove, hey, a vulnerability exists.
So they just need to get lucky once.
Exactly. But FAPO is operating under a much heavier burden. It isn't looking for one lucky run. It has to mathematically improve the mean score of a specific pipeline variant across N evaluation cases. It has to explain recurring failures.
Yeah, which demands actual diagnostic attribution. You can't just throw spaghetti at the wall and see what sticks.
Right. So how does it actually pull that off?
So to achieve that level of consistency, FAPO relies on a 5-step optimization loop driven by Claude Code. And the mechanics here are what allow it to actually rewrite your architecture safely.
Okay, walk us through the loop.
Step 1 is evaluate. So FAPO runs the current pipeline on a training split, but it doesn't just record the final answer. It records all the artifacts like the inputs and outputs of every single intermediate step.
Oh, so it has a complete paper trail.
Exactly. Then step 2 is attribute. It diagnoses failures on a per-step basis. Like, did the retrieval search return empty? Did the formatting step just drop the JSON schema?
Oh, that makes sense.
Then step 3 is propose, where it suggests exactly one scoped edit to fix that diagnosed bottleneck. Step 4 is review, which acts as a really stringent safety gate. And step 5 is compare, where it tests the new variant against the validation aggregate to confirm the score actually went up.
Now, that kind of orchestration requires some pretty specialized personas, right? Because FAPO doesn't just give Claude Code a generic instruction.
No, not at all. It deploys 3 specific agents working in concert.
Okay, what's the first one?
The first is the optimization agent. This serves as the orchestrator. It reads a tenant playbook, decides on the allowed optimization points within your specific code base, triggers the evaluations, and formally proposes the edits.
Okay, and the second one?
Sitting right next to the orchestrator is the step attribution subagent. This is basically the diagnostic engine. It takes the evaluation results, logically clusters the failures, and makes this crucial decision: is this failure prompt addressable? Meaning, can we fix it by changing the text instructions?
Or is it structural?
Exactly. Is it a structural bottleneck?
Yeah.
Like, can we fix this with words, or do we need to actually write new Python code?
Right.
And then finally, you have the variant reviewer subagent. This operates as an independent safety gate. It aggressively checks the scope of every proposal before it gets executed.
And I've got to say, putting my ML engineer hat on for a second, giving an AI autonomous script access to rewrite pipeline code and prompts in an automated loop, that sounds terrifying.
Oh, it absolutely does.
Like, I immediately see a scenario where this thing wildly overfits to the training data. Or worse, accidentally leaks test data into the training process and fabricates a high score. Because, if an AI has access to the code base, it has access to the evil scripts.
Yeah, that's the classic fear. But the variant reviewer subagent exists almost entirely to prevent that nightmare scenario. And it's backed by rigid system architecture.
How rigid are we talking?
Very. FAPO enforces split access control. The optimizer agent only ever sees individual training cases. The validation and test sets are physically isolated. They're completely hidden from its context window.
So what does it get back from validation?
The system only gets aggregate scores back, literally just a simple numerical value.
Right.
It cannot memorize the test data because it simply never sees the test data.
Okay, but even with data isolation, an autonomous agent tweaking Python files could turn a clean repository into just a tangled mess of broken functions and overwritten logic. You could wake up to a codebase that doesn't even compile.
And that's why FAPO solves this through variant immutability. The agent is strictly prohibited from overwriting any existing file.
Oh, okay.
Yeah, every single proposal, whether it ends up being accepted or rejected, is saved as a brand new, isolated variant file. You maintain a perfect, immutable Git history of every hypothesis the agent ever tested.
That's relief.
And alongside that, FAPO enforces absolute isolation between tenant workspaces. An optimization run for a specific text extraction task cannot leak context or Python classes or prompt snippets into another task's workspace.
So it's heavily sandboxed.
Exactly. That structural discipline is really the only reason this functions safely in a standard enterprise code base.
And that discipline allows FAPO to execute what I think is its most powerful feature, the escalation strategy.
Oh, definitely.
Because the framework operates on this principle of the smallest useful change. It will always start with prompt optimization, because changing a text string is, the cheapest, least invasive intervention available.
It's the path of least resistance.
Right. And it only crosses the boundary into software engineering, like modifying chain parameters or rewriting the actual LangGraph structure if 2 strict conditions are met. First, the scope contract you define for that tenant has to actually allow code edits.
Which is an important guardrail.
Right. And second, the step attribution subagent has to definitively prove that a structural bottleneck exists, meaning a prompt edit simply cannot solve the problem.
Yeah, and you really see the magnitude of that capability in the Hover benchmark.
Remind me what Hover is.
So Hover is a many-hop fact verification task. The pipeline has to verify a really complex claim by hunting down evidence spread across multiple disparate Wikipedia articles. And the baseline pipeline FAPO was used a standard 3-hop retrieval chain.
Which, a 3-hop chain is a very logical baseline for a retrieval task. I think most human engineers would start exactly there.
They absolutely would. But FAPO's attribution agent looked at the intermediate artifacts of the failed runs and realized that 3 hops physically lacked the depth to retrieve the necessary context for the hardest questions.
Because the answers just weren't there.
Exactly. The LLM was failing because the answers simply weren't in its context window. And no amount of clever prompt engineering can force a model to verify a fact it cannot see.
So FAPO escalated.
It escalated. It physically rewrote the Python code defining the pipeline and extended the chain to 4 or 5 hops. But the mechanism of the fix is what's really brilliant here.
What did it do?
It didn't just passively add more of the same semantic search steps. It introduced multi-query BM25 search and entity-aware rescue mechanisms directly into the graph architecture.
Wait, BM25, that's a classic sparse keyword-based algorithm. FAPO basically realized that when the LLM's dense semantic reasoning couldn't find the right conceptual match, the pipeline needed a hard fallback to simple keyword matching to rescue the data.
Exactly.
It literally coded a failsafe into the system, and the impact of that structural change is staggering. FAPO drove a 24.78 to 48.56 percentage point gain on that benchmark, depending on the model.
A near 50-point jump.
Yeah, entirely, because the agent diagnosed the graph architecture itself as the limiting factor. That is wild.
And we observed the exact same phenomenon on IF-Bench, which is a verifiable instruction following benchmark.
How so?
Well, the pipeline in IF-Bench has to output answers following incredibly strict formatting constraints. And FAPO analyzed the failure clusters and identified that the models were actually generating the correct facts.
But they were failing anyway.
Yeah, they were failing the benchmark purely due to formatting errors in the final output. So instead of loading the prompt with desperate please telling the LLM, please strictly follow this exact JSON schema, or else FAPO physically added deterministic post-processing nodes to the LangGraph chain.
It just wrote code to fix it.
It wrote Python functions to strictly enforce the formatting constraints on the LLM's output. And that single structural intervention resulted in 19.84 to 38.95 percentage point gains.
See, it is just an incredibly pragmatic approach to AI engineering. Like, if the probabilistic LLM is inherently bad at strict formatting, just write a deterministic Python function to format it.
Right. Don't force the LLM to do everything.
Exactly. Stop wasting valuable context window tokens trying to prompt engineer your way out of a standard software problem. By crossing the boundary between text generation and pipeline engineering, FAPO stops treating the LLM as a magical, monolithic black box that must do everything flawlessly.
This is a tool.
It treats the model as just one component within a broader software system.
And that philosophy really brings us to the granular model asymmetries the paper uncovers, which are, frankly, fascinating.
Oh, the model comparisons. Yeah, let's get into that.
So FAPO was evaluated across 3 distinct models: GPT 4.1 Mini, GPT 5.4 Mini, and GEMMA 312B. Even when restricted to prompt-only comparisons, so no structural edits, FAPO's iterative loop beat GEPA in 9 out of 12 head-to-head matchups.
Right.
But there was one glaring anomaly in the data, and that was the AIM benchmark.
Which is the high-level competition math benchmark, right? Requires deep, multi-step symbolic reasoning alongside rigid formatting.
Exactly. And it was the only test where the baseline GA optimizer consistently outperformed FAPO across all the models.
And the paper is remarkably transparent about treating the A results as inconclusive. Their analysis basically suggests that FAPO may have overfit to the small sample sizes provided in the training split.
Right, especially relative to the massive problem space of competition-level math.
Yeah, because in a highly discrete search space, an evolutionary algorithm like GPA's and MyProf2 can sometimes just stumble upon a highly robust, generalized instruction string that an agentic, logically driven loop might miss. Because, the agent is trying to overly tailor the fix to the specific failures it just saw.
It's a classic case of overfitting to a local minimum. But honestly, the AIM anomaly pales in comparison to the most alarming technical question buried in these baseline metrics.
You're talking about the GPT 4.1 versus 5.4 thing?
Yes. If you look at the raw baseline scores across these benchmarks, the older GPT 4.1 mini model actually outperformed the newer, highly capable reasoning model, GPT 5.4 mini, on 4 of the 6 tasks.
And obviously, a surface-level read of that data suggests the benchmarks are broken, or, the newer model is somehow regressing in its capabilities, which is a huge question for anyone tuning in. How does an older model beat the newer one on baselines?
Yeah, it's easily one of the most vital insights for any ML practitioner working with modern reasoning models, because the discrepancy fundamentally comes down to how token budgets are accounted for under the hood.
Okay, unpack that for us.
Well, in the baseline setup, both models were given an identical 16,000 token limit for generation to keep the evaluation fair.
That sounds fair on paper.
It does. But the fairness is an illusion based on the architecture of the models. For GPT 4.1 Mini, that 16,000 token limit applies exclusively to the visible output tokens it generates.
Okay.
But GPT 5.4 Mini is a reasoning model. It generates a hidden reasoning trace before it outputs the final answer. So that 16,000 token budget is actually a shared pool. The model has to spend tokens from that exact same budget to think before it can spend tokens to write.
So if the model encounters a difficult problem and thinks for a long time, it literally cannibalizes the tokens it needs to format the final answer.
Yes. On long derivation tasks like live bench math, GPT 5.4 Mini would spend thousands of tokens in its hidden reasoning phase. And by the time it finally arrived at the correct mathematical conclusion, it would hit the token ceiling and abruptly stop generating.
Oh, wow. So it just cuts off.
It cuts off. FAPO's logs revealed that on live bench math, GPT 5.4 Mini's median visible output length was a meager 78 tokens. It was spitting out malformed, truncated final answers.
And because these technical benchmarks use rigid, exact match parsers for evaluation, a truncated answer is just a failed answer.
Exactly.
If the model outputs the correct complex derivation but lacks, like the final closing bracket required by the exact match parser, it scores a 0. The parser does not care how brilliant the hidden reasoning trace was.
Nope, 0 credit. But FAPO's attribution agent identified this mechanical failure immediately. To make GPT 5.4 Mini competitive, the optimization loop realized it had to systematically increase the model's token budget.
It pushed it up, what, to 24,000?
Up to 24,000 or even 28,000 tokens. It gave the model enough runway to finish its hidden thought process and still execute the required formatting constraints.
Which is brilliant because a human engineer skimming those baseline scores would naturally conclude that GPT 5.4 Mini is just worse at math. But an automated system examining the step-level artifacts realizes the model is just suffocating under an artificial token constraint.
It proves exactly why optimizing the pipeline as a whole is mandatory for modern models. You have to look at the intersection of model behavior and parser requirements.
Absolutely. And this principle is tested to its absolute limit in the final major domain FAPO tackled, which was cybersecurity. Specifically, the CTI bench RCM task.
Right, which represents a highly rigid enterprise-scale classification problem. RCM stands for root cause mapping.
Yeah, and for context, the pipeline is fed a CVE, a common vulnerabilities and exposures description detailing a security flaw, and it must map that description to one specific CWE, or Common Weakness Enumeration ID.
And this is not a simple multiple-choice question. It is a 263 classification problem. The formatting has to be flawless.
So to see what FAPO could do in a restricted environment, they locked it in a box for this task. They constrained the agent to prompt edits only. No Python scripts, no LangGraph structural rewrites.
Just words?
Just words. And even fully restricted, FAPO improved test accuracy across the board. It secured a 4.0 percentage point lift for GPT-5, a 7.1 point lift for the Foundation Sec 8B Instruct model, and a 2.0 point lift for the Foundation Sec 8B Reasoning model.
The raw score improvements are impressive, but honestly, the mechanism behind them is what shatters our assumptions about prompt engineering. We see a radical divergence in what constitutes a good prompt, dictated entirely by the underlying weights of the specific model.
The prompt size differences were crazy.
Yeah. So for GPT-5, FAPO determined that the model thrives on extreme specificity. It took a simple 4-line baseline instruction and expanded it into a dense 23-line prompt. FAPO injected highly specific rules derived from National Vulnerability Database conventions directly into the context.
It wrote a textbook.
It essentially wrote a mini rulebook, explicitly telling GPT-5, if the vulnerability involves a buffer overflow, you must output CWE 787, not CWE 121 or 122.
Which makes sense. For a massive model like GPT-5, adding edge case instructions works beautifully. And as human developers, we intuitively assume that giving a system more specific rules will inherently improve its accuracy.
Right, we always think more detail is better.
But FAPO proved our intuition completely wrong when it optimized the smaller Foundation Sec 8B Instruct model. Because when FAPO attempted to feed those exact same dense rules to the 8B model, performance degraded. The model got confused by the complex context and its format extraction completely broke down.
It overwhelmed it.
Yeah. So through its iterative evaluate and attribute loop, FAPO systematically stripped the prompt down. The highest performing prompt for the 8B Instruct model turned out to be a heavily reduced, ultra-minimalist 2-line prompt.
Which is just the ultimate validation of FAPO as a framework. Human engineers have a singular, inherently biased mental model for how to solve the problem. We operate under the assumption that more detail equals better results.
We think we know what the model wants.
Exactly. But an automated, evidence-grounded loop has no ego and no assumptions. It runs the evaluations, looks at the artifacts, and blindly follows the data to discover the highly idiosyncratic strategy that a specific set of model weights actually responds to. It figures out that GPT-5 needs a textbook, while the 8B model just wants to be left alone with a simple command.
It is a really humbling realization. The best prompt engineer isn't a person agonizing over adjectives. It's a diagnostic system that can run 50 variants, analyze the exact token outputs against an exact match parser, and mathematically prove what works.
Yeah, FAPO gives ML practitioners a reproducible, evidence-grounded workflow that finally bridges the gap between text-level prompt engineering and structural pipeline engineering. It stops treating AI development as a black art.
And starts treating it like software engineering.
Exactly. It forces us to acknowledge that multi-step AI pipelines fail in incredibly complex, interrelated ways. And FAPO provides a systematic, autonomous way to debug and optimize those interactions. It basically operates as a tireless, data-driven junior engineer that lives in your code repository, analyzing failures and pushing Git commits to fix your architecture while you sleep.
Which leaves you with this incredible provocative thought to mull over. If a system like Claude Code can already analyze intermediate step failures, identify structural bottlenecks, and safely rewrite a pipeline's Python architecture during the development phase, you really have to ask how far we are from self-healing AI pipelines in production.
That's the logical next step.
Right. Imagine deploying a compound AI system that automatically monitors its own live user failure data, traces a hallucination back to a specific retrieval step, and dynamically rewrites its own line graph architecture in real time to fix the bottleneck, entirely bypassing the human engineer.
That would change everything.
It really would. And the tools to build that future are already functioning in the codebase today.